and the public can leave questions. On the online on those links. Just type the questions at the public.
Okay.
And the public also, I recommend the public have questions, and at the end, we are going to read the questions and transmit to you. Perfect. Okay. Melvin, ¿ya estamos en línea?
Sí, profesor, ya estamos iniciando la grabación en el Meet. Un momento para el otro.
Ya, ok, nos avisas. Nos avisa. It's not online yet, it's just recording.
Okay.
So. I will speak in Spanish and in English, in both, because it's the Latin American audience for the public, and also in English for you and also the rest, okay?
Thank you, yes, thank you.
Yeah, both. You can give your talk in Spanish or English, depends on you. Or in Portuguese as well, depends on you.
Okay. I think better in English.
Yeah.
Sorry, Luis. I'm Portuguese. Or Portuguese.
Or in Portuñol is one. Depends on you. Okay.
Thank you.
Thank you. Okay. Bueno. Eliana, ¿también ya está casi listo para hacer la transmisión en línea por las otras redes? Okay, there are some... Okay, ready. We start. Good morning. Good morning, everybody. Good morning, the Latin American audience. This is the network of LAFMAT. Buenos días a todos. La red latinoamericana de física de materia condensada y ciencias materiales, red LAFMAT. El día de hoy tenemos la presencia de una invitada muy especial, la doctora Michelle Villamayor, que conocí en la Universidad de Filipinas, en Manila. Actualmente, la doctora Michelle Villamayor se encuentra trabajando en el Central Mindanao University. El día de hoy tenemos la Bukidnon en Filipinas. La charla que va a dar el día de hoy la doctora Michelle Villamayor es Plasma Technology. Doctora Michelle Villamayor, Deposition and Surface Modification. La doctora Michelle Villamayor es doctora en física, estudió el pregrado y el doctorado en física en la Universidad de Filipinas, en Diliman, Quezon City, en Filipinas, Manila, bajo la supervisión del profesor Henry Ramos, un gran amigo mío. Luego hizo postdoctorados en las universidades de en Uppsala University, en Suecia, y también en Grenoble, en Francia. Ella se especializa en lo que es plasma, también en sputtering, en óxidos, nitridos, carburos, sulfuros, etc. Doctora Michelle Villamayor se encuentra Doctor Michelle Villamayor, carburos, sulfuros, etc. Field sputtering material science focuses on various thin fields of oxides, nitrides, carbides, sulfides. She studied in the University of the Philippines in Manila, Philippines, and did she studied there undergrad and also her doctoral studies. Then she moved to Sweden to do a postdoc in Sweden in the University of Uppsala. As well, she did another postdoc position. She has been a researcher and in Grenoble in France. The talk of Dr. Michelle Villamayor today is Plasma Technology for Thin Film Deposition and Surface Modification. La charla de la doctora Michelle Villamayor el día de hoy es Plasma Technology for Thin Film Depositions and Surface Modification. Bien. Bienvenida. Welcome, Michelle Villamayor. It's very nice to see you here in this Latin American network of Material Physics, Matter Condensing Physics. Doctora Michelle Villamayor, el día de hoy es Material Science, and which is confirmed for many universities in Latin America. The University of San Sebastián in Puerto Montt, Chile, the Catholic University in Antofagasta in Chile, the University of Pernambuco, Recife, Brazil, University of Rural Federal University of Rio de Janeiro, University of San Marcos in Lima, Peru, University of Colombia in Bogotá, University of Zulia in Venezuela, Cimbestap of Mexico, and many University of San Martin, Argentina. And this your talk will be streamed in many Latin American universities, and the public can follow in different links. And the public can leave their questions online, and at the end of the talk, Dr. Michelle Villamayor is going to reply. Okay, thank you, Michelle. Welcome again, and you can start your talk. You can present as well. Thanks.
Buenos días, amigos, y buenas noches aquí en Filipinas. I will be giving my talk in English. So let me just give a moment to share my screen. Can you now see my screen?
Yes, it is uploading. Yes,
Okay.
we can see.
All right. So good evening, everyone. My name is Michelle Marie S. Villamayor, and I'll be presenting to you from here in Bukidnon, Philippines. So yes.
We cannot see your slides.
Okay. You can see or you cannot see.
We can see your screen, but the Google Meet screen, but not your slides.
Okay. Give me a moment, please. How about this time? Can you see my slides?
Yes, now we can see.
Okay, so I'll just move to presentation mode. How about this one? Can you see my slide?
Yes, we can see your slides. Go ahead.
Okay, so good morning, everyone in Latin America, and good evening here in the Philippines. I also have invited some guests to watch over my talk. So as Professor Luis mentioned, so I did my education here in the Philippines. So the Philippines is in Southeast Asia, and I was an exchange student researcher in Doshisha University in Japan. And when I finished my education, I moved to Europe to do my postdoc in Linköping University in Sweden first, and then I moved to France in CNRS. And then I moved back to Uppsala University as a researcher. After my contract ended in Uppsala University, I moved to Chromogenics AB, a private industry, and worked there as a project engineer for almost 1 year. Last year, I decided to come home and work part-time for De La Salle University, which is also in Manila. I worked online because of the COVID pandemic. However, I decided to join fully face-to-face Central Mindanao University in Southern Philippines by September of 2022. For the meantime, we are currently collaborating with Ionotics AB. It's a private company creating high PIMS power supplies in Sweden. And we are also strongly in collaboration with Ateneo de Manila University, Mindanao State University, IIT, University of Science and Technology of the Philippines, and also the University of Southeastern Philippines. We also recently applied for funding together with the National Sun Yat-sen University of Taiwan. So before I proceed, let me just talk a little bit about the Philippines. So the Philippines is an archipelagic country here in Southeast Asia, and it is composed of 7,641 islands as of the moment. So the better resolution cameras we have, the more islands you can see in the Philippines. It also depends if it's high tide or low tide. If it's high tide, then there's less islands that are available. And also, the country is about 109 million in population. And all over the country, there are more than 120 languages spoken. So it's very natural for us here in the Philippines to be able to speak at least two languages. So for me, when I was growing up, I can speak my local language, which is Cebuano Bisaya. I also learned the national language, which is Tagalog Filipino. And for us, it was a requirement to learn English. So back then, the people learned Spanish. However, during the 60s and 70s, the government decided that we shift to English instead. So my parents and my grandparents, they can speak Spanish, but for my generation, we speak English predominantly instead. For this photo, this is the Philippine flag. And if you are going to show the Philippine flag, you have to be careful putting the blue band and the red band. So if the blue band is on top, it means we are at peaceful times. However, if you mistakenly put the red band on top, it means that the Philippines is during the wartime conditions. So since we are during peaceful times, the blue band is on top. And on this next photo is the Bukidnon capital. So Bukidnon is the province where I grew up and now where I live. And this is the capital grounds on the picture. Here is Malapascua Island. This is an island in central Philippines, and it's a photo I took last summer when I was on vacation. And this month, we will be celebrating the Kaamulan Festival. It's a yearly celebration where we give respect to our inheritance, and these are celebrating the 7 tribes of Bukidnon, and we call this the Kaamulan Festival. So about the university is called Central Mindanao University. It was founded in 1910, predominantly as an agricultural school. And right now, we are serving more than 16,000 student enrollees. And since it's an agricultural school, it was decided long time ago that it will own and operate 3,080 hectares of land, which was granted by the government. So take note that 1 hectare is 10,000 square meters. We are composed of 9 colleges, and I belong to the College of Arts and Sciences. And we serve the BS Physics program, which was started in 2013. Now, the faculty of the BS Physics program are predominantly aligned to the materials science field. As for the photos, you can see here the administration building and also the iconic fountain in front of the admin building. And on the bottom, this volcano right here is actually part of our land, and this last erupted in 1886. Around it is surrounded by mostly land which can be tilled and used for agriculture. So without further ado, let me start with my abstract. So I will talk mostly about plasma sources. These are the sources that I used while I was studying, while I was doing my postdoc. And towards the end of my talk, I will be showcasing to you the projects that we have done in Central Mindanao University. It will be related to thin film deposition and surface modification. So let's talk first about plasma. What is plasma? Well, plasma is the 4th state of matter. This is not the blood plasma that we usually hear. We're talking about the 4th state of matter. So for example, we have solid, let's say ice, and then you expose solid to high energy or high temperature. Then there's solid turns to liquid. Further exposing it to higher energy, this liquid turns to gas. Now, example, if we have a gas which is exposed to more energy, let's say electromagnetic radiation, if the parameters are enough, then our gas gets excited into a plasma. What do I mean? So for our gas, we have an atom, and our atom is composed of neutrons and protons, and surrounding that is our electrons. Now, if the energy is strong enough, our electrons gets kicked out of the atom, and then now we have an ion and also electrons. But in some cases, the energy is not enough to kick out the electrons from the atom, but it gets excited to a higher energy state. Now, when this energy is lost, the higher energy level of the electrons goes down, and when this electron energy level goes down, photons are emitted. These photons are light, and this is what we see as plasma. Now, more than 99% of the visible universe is made up of plasma, and examples of naturally occurring plasmas are the stars, the sun, the nebulae, and the auroras. In our atmosphere, it is difficult to create naturally occurring plasmas, but we can see them around us using tools and devices. So, for example, the fluorescent, what we see there is a plasma. We also have the plasma TV and even the neon lights. These are also plasma. So how does this fluorescent lamp work? Now, the fluorescent lamp is actually a vacuum tube. It means that we have a tube of glass, and then we evacuate it. We take away the air inside of it and replace this air with mercury gas. And then the sides of this vacuum tube are electrodes, and inside of the vacuum tube is phosphor. So we line it with phosphor. Now, if we turn on the electricity, so the electromagnetic wave goes through the electrodes, and this electromagnetic wave will excite our mercury gas. Our excited mercury gas attacks the phosphor, and the phosphor is the one that lights up, and that is why we see white light from the fluorescent lamp. As for the plasma TV, imagine this vacuum tube being created into very, very tiny pieces, and that is the pixel on our screen on the plasma TV. And these pixels are then arranged or are created into an array which gives off light. And then if we move backward, we see an image in front of the plasma TV. Now, the last example that I'm going to show you for commercial plasma is the neon light. So it's also a vacuum tube, and it's connected to a neon light transformer, and this transformer is the one that excites our neon gas, giving off the neon lights. Now, the same transformer is actually used to ignite our atmospheric pressure plasma jet. I will give the application of this atmospheric plasma jet towards the end of my talk, but for the meantime, you can look at the actual image and also the schematic. So this is actually small. It's almost the size of your hand or the size of your palm. And it is composed of two electrodes. These are two tungsten electrodes almost touching each other, but not touching each other. And then they are connected to the neon sign transformer. And on top of this tube is a gas inlet where we pass compressed air. And once compressed air is passing through these powered electrodes, we can actually see the discharge region. So here on the schematic, we see the discharge region, and outside the nozzle is the plasma jet, and here is the small opening where the plasma passes through. Okay, so this is how the atmospheric pressure plasma jet works. We could also ignite plasma inside a vacuum chamber. And this one is an example of that. It means that we have evacuated this chamber with air, and we replace it with high purity gas, for example, argon. For this chamber, this is the size of a large hamburger, and I have actually put it side to side with a coin, a 100 yen coin. It's a regular size coin, and this is very common in Japan. So I used this device when I was a master's student. And for this device, we actually used water vapor. We excited water vapor to create zinc oxide. The plasma looks like this one. You can actually ignite the top portion and the bottom portion, but for this image, we only ignited the top portion. So schematically, this is how it is designed. So inside the chamber, we have the target. That's going to be our zinc source or zinc metal source. So we have one target on top and we have one target at the bottom. And then behind our target are magnets. And our magnets help trap the electrons, thereby increasing the chances of the argon. So we also introduce argon inside. These argon ions are the ones that are going to sputter out the target, and the sputtered out zinc target gets deposited onto our substrate. Now, if we introduce water vapor, H2O, the H2 and the O gets separated and the oxygen reacts with the zinc, and we are now able to deposit a zinc oxide onto our substrate. Now, depending on the parameters, if the parameters are not correct, for example, if we introduce too little water vapor, then we end up with depositing zinc on our substrate instead. So this is how it looks like, because we did not introduce too much H2O. We ended up with a zinc foil, a highly opaque zinc foil on top of our glass substrate after magnetron sputtering. Now, if we are not careful, sometimes this zinc target will also get melted. And that is one problem that we have to deal with when doing experiments and if we don't know the proper parameters. Moving on, the technique that I learned in Japan was brought here to the Philippines, where I made my own magnetron sputtering device. And this device was my ticket towards my PhD graduation. So let me zoom in a little bit. So instead of water vapor, we used high purity argon and high purity oxygen. The flow is controlled by a mass flow controller. And this mass flow controller decides how much flow we are going to put inside the chamber, and also what is the ratio between argon and oxygen. Now, the target is here at the bottom. It's connected to a negative bias power supply, and the chamber is connected to a pump source. This is a duo rotary and a turbomolecular pump. Now, here, if we look closer, we have the substrate and also the target, and the plasma is here, where we sputter out the target, which is titanium dioxide. And the target is titanium. It reacts with the oxygen, and then we are able to deposit titanium dioxide. Now, the device looks like this. And for this example, we have the dual source. So both the targets are turned on. So we have a source at the bottom, we have a source at the top. This helps increase the sputtering yield, and also if we would like to deposit on both sides of our substrate. We have actually produced a publication together with Dr. Luis using this study. We used this titanium dioxide to kill bacteria. So we tested a sample without titanium dioxide, and we tested a sample with titanium dioxide, and then we also exposed it to UV because TiO2 becomes bactericidal together with UV. And we have shown that if you deposit titanium dioxide onto your sample and then expose it to bacteria, we can see a lot of inhibition growth. Whereas if we do not deposit TiO2 onto the glass substrate, then the entire Petri dish is full of bacteria. I would also like to introduce to you the sheet plasma negative ion source. So the previous example, we used magnetron sputtering technique, whereas here we use something called thermionic emission to create the sheet plasma negative ion source. So what does that mean? So in this chamber, we actually have two parts. We have the plasma production chamber here, and then towards here is the plasma extraction chamber. So we create plasma at the production chamber, and then using a series of electrical wires and magnetic field, we can actually guide the plasma from the production region towards the extraction region. In order to create the plasma, we use a tungsten wire and we introduce it to high voltage. Now, this high voltage will force our electrons to get kicked out from the metal surface, and this is called thermionic emission. These electrons are then used to ignite the argon gas, which becomes argon plasma. And then the argon plasma is guided towards the extraction chamber. It sputters out the titanium target, and the titanium material reacts with the nitrogen, which was also fed here in the extraction chamber. With this one, we are able to deposit titanium nitride hard coating thin films. So in the picture is my former professor, Professor Henry J. Ramos. He was my teacher from bachelor's, master's until I finished my PhD. He actually designed the sheet plasma ion source with the chamber as fully made of glass. However, if you are dealing with plasma, you have to tighten the source, and then the regular use of tightening and then breaking it out and then tightening it again will break the glass. And it's very expensive to bring it to San Miguel Corporation. And San Miguel Corporation is actually a bottling company. They also produce beer here in the Philippines. And so Dr. Henry Ramos applied for funding to change the glass chamber into an all-metal chamber. And then later on, he was able to commercialize this and double the size of the extraction chamber, which was then used by a company to deposit titanium nitride hard coating thin films. So this was him when he was starting in 1989, and this was him in 2012, almost 11 years ago. These are some sample deposits we were doing when we were optimizing the deposition of TIN. And here is how the plasma looks like. So one of the problems with plasma deposition is the non-uniformity of the sample, and you have to tweak that, and you have to change where the target is going to be placed, where the gas is going to be fed, and how you are going to create the plasma. Now, there's another way of creating plasma, and this is called microwave-assisted physical vapor deposition. This time, we use microwave sources on the side, and then this ignited argon-oxygen plasma sputters out the vanadium, and the sputtered vanadium reacts with oxygen to deposit vanadium oxide or vanadium dioxide onto the substrate. It's very important to heat up the substrate if you want to deposit VO2, otherwise we end up with different oxidation of vanadium. And for this size, it's almost half the size of a person. This is a good friend of mine. She was my colleague in Grenoble, France. And I took a photo of her so that it will be easy to see the size of this device. Now, vanadium dioxide is an interesting material because it's a metal insulator transition material. It means that at certain temperature, it acts as a metal, and at other temperatures, it acts as an insulator. So for vanadium dioxide, for temperatures less than 68 degrees, it's an insulator. So you can see here, this is the resistivity, which is in ohm centimeter. At lower than 68 degrees Celsius, it has a very high resistivity. However, if you subject this material to higher temperature, it transitions to being a metallic material. However, if you take away the heat and cool it down, the resistivity goes up again. And we have this hysteresis here, which scientists are trying to get rid of. And also, it's very important for this transition temperature to go down to be able for this vanadium dioxide to be commercially useful, especially in aerospace application. So how did we make sure that it's the same material? We also did other tests. For example, we checked its Raman response, and we also did X-ray diffraction. And this is an SEM image of the film. So for the Raman response, we saw that at low temperature, the material gives off a signature Raman peak, which is insulating. However, at high temperature, or beyond the transition temperature, we have a flat response, which means that the material is metallic. For Raman, it behaves when the vibration of the electrons are excited, and if the material is insulating, it will have these signature peaks. However, if it's metallic, it will have a flat response. And we did this by heating up the material slowly, and we also measured the response after we cooled it down, and it did indeed go back to this 25 degrees Celsius signature. We also checked for its XRD peak, and it's very, this particular position right here indicates that we have a transitioning material. So we have a VO2 R phase, M1 phase, and M2 phase, where the M2 phase is the transitioning, it's in between the R and the M1 phase. So that was for vanadium dioxide. Now, vanadium dioxide, it's also blocks infrared, and that's why it's interesting. But another type of material which blocks light is actually a sandwich of two electrochromic layer and an electrolyte. Now, this time we are in Sweden, and here I will show to you how do these chromogenic windows work. So you can see a window to the left and another window to the right. So the window to the left is actually turned off, meaning it allows light to pass through. However, on the window to the right is turned on, and you can see that it has changed opacity. And how is it made? How is it made? So we actually have a polyester which is deposited with an electrochromic layer nickel oxide, and then we also get another polyester where we deposit tungsten oxide. And then in between these two polyesters with metal oxide deposit is an electrolyte. Now, once these two are sandwiched together, we put it inside a glass. And this glass now becomes our window. Now, the question is, how do you deposit this oxide layer onto this polymer? And the answer to that is roll-to-roll sputter. So this device is about 180 tons. It was a device which was designed and used for solar cell deposition in Germany. However, the company bankrupt and they decided to sell this, and the Swedish company Chromogenics decided to buy this in 2019. Then they moved this device by land from Germany to Sweden and decided to house it in this huge warehouse building. Unfortunately, this device is too large for the door. So in order for this device to go inside the building, they had to destroy the roof, or they have to open up the roof and then use this large crane to put it inside. I was not working in this company when this happened. I joined them later on. Okay. So in 2001, I was lucky enough to be chosen as their production engineer. And I was there to optimize the process. I was also there to train some of our students. So these two students are working students from Pakistan, but they were doing their masters in chemistry and mechanical engineering in Uppsala University. These two Filipino girls are, she was doing her master's in agriculture in Uppsala, and this girl, she's also Filipina. She was doing her bachelor's, finishing her bachelor's, and we also met in Uppsala, and I was showing them around how the machine works. These two are full-time workers in chromogenics. I also taught them how to operate the device, and this is how the roll looks like. So this one is untreated. It did not have any metal oxide yet. And what he's trying to do is trying to align the roll so that it doesn't, it goes smoothly through the chamber. Because the problem, if there is misalignment, then the deposits are going to show waves, and these waves are not going to look nice onto the processed window. Okay, so you see that they are using these suits. So they are trying to avoid any hair to fall down onto the samples, and they are also trying to avoid any of the oils from their hand touching the samples to in order to increase the vacuum time, or I mean, so that they don't have to wait too much for the pressure of the vacuum to go down. However, there are some chambers which doesn't need to be clean. So one example of that is if you are going to deposit 2D sulfide metals, for example, tungsten disulfide or molybdenum disulfide. The reason for this is these items here, they actually become a sponge of sulfur. And if we are going to do a deposition, the sulfur sort of gets released from the sponge and helps in the deposition of the 2D layered material. And using sputtering, we were able to deposit these 2D metal sulfides onto a 4-inch wafer. So it's still magnetron sputtering. So we also have a target. There's magnets at the bottom, which we did not show anymore. The samples are heated at high temperature, up to 700 degrees Celsius. And we also introduced H2S and argon. So the sulfur here is the one that we use to help create the tungsten sulfide, even though our target is already tungsten disulfide. And as you can see, we have a very uniform deposit of this material onto our silicon substrate. Now, we tested how many layers of tungsten disulfide was there on our sample, and we used Raman to do that because for Raman, there are signature peaks, and if the separation is at certain distances, then we know that this is 1 layer or 2 layer or 4 layer of tungsten disulfide. And we have tested the monolayer, bilayer, 4 layers, and 8 layers. And in summary, we have all of these results here. So we checked for a particular peak, and if the peak separation is small, then we know that it's a monolayer, and we have compared our results to other publications. So for us, for the monolayer in the 4-inch wafer, we have found that our results are the same or almost the same with the published results, which are in theory and also done in experiments. And here on the gray bar is actually the separation, peak separation distance of these 2 Raman peaks, which indicates monolayer. And this gray bar is this Raman map. Unfortunately, there was one point which we did not have any information, but for the rest, we have a reliable 1-layer deposition onto the sample. We created we have gathered a cross-section TEM image or transmission electron microscope image of several layers of tungsten disulfide. We have tried to check the TEM of a monolayer and a double layer. However, it was very difficult for our technician to do so. So what we did was to create multi-layers of this material and made a TEM of this instead. So now we are going back to the Philippines, and our research in CMU started in October 2023. I personally financed the startup of our project because it was too late in the year for funding applications, and I had 2 physics students who are supposed to graduate this year in April or in May. So we bought a low vacuum plasma system, or we made our own low vacuum plasma system, and also we made our own atmospheric plasma. So for the design of the low vacuum plasma system, I used the one that I did when I was doing my PhD, but we didn't have the high-end vacuum pumps. And for the atmospheric plasma, the design was shared to me by my former colleague and classmate, Dr. Christian Mahinay. And so my students started working on this. So it's very rough. We don't have a dedicated clean room. So we have some extra rooms where we decided, okay, we're going to build the lab here. And I bought this hobby type for um, for polymer making. It's a hobby kit which has a single stage rotary pump and a vacuum chamber. And for the gas sources, I was quite worried that we couldn't find high quality or high purity gases. However, I found Linde in the province. Apparently, the business boomed because during the pandemic, people were ordering a lot of oxygen tanks. And so Linde was able to create a shop here in Bukidnon, and they were also selling high purity argon and oxygen. As for the atmospheric plasma jet, so as I told you, the size of this tube is almost the size of a palm, and my student here, Jay, is actually very happy because it already arrived. And he's actually holding that. It's hard to see, but he's holding it and it's on the palm of his hand. So let's start with the low vacuum plasma. So instead of creating it for epoxy hobby, I have changed it, or I have modified it to create a vacuum chamber. So using this single stage rotary pump, it's attached to the top. And then we have created a hole at the bottom. So this is going to be our gas inlet. And we created some cooling. So we just used flowing water. We didn't have a chiller because it was too expensive. And we tried to ignite this with the help of our collaborators from the USTP, University of Science and Technology in Southern Philippines. And we were able to ignite our first plasma last November. Oh, sorry. Let me play that again. So we were able to ignite that and we were happy. Unfortunately, towards the end of this video, the power supply started to smoke. We had to turn it off. And then when we tried to ignite again, it was not igniting. So we came up with a conclusion that it was difficult to obtain a glow discharge magnetron sputtering without sacrificing our homemade power supplies. So we tried to modify it to create an arc discharge. So we put some copper wires here connected to the ground and one that is negatively biased. And the thing is, since we didn't have proper cooling, the Kapton tape was melting around it for insulation. So we used electrical tape because it didn't melt. However, this is a bad practice, especially for our vacuum technologists, because this electrical tape, they are actually causes for contamination. But for our experiments and for whatever we have available right now, I said, yeah, we can use it for the meantime. And we were able to ignite this arc discharge.
I'm gonna turn this on. Yeah. Whoa! Whoa! What? Whoa! Whoa! What do you mean? Plasma there, dude. Wait, 30 seconds. Ilan to sing? 30 so good. 30 so good. Wow! 30 seconds lang. Apa? Oh. Pag 2 minutes ni. 2 minutes lang. Wala pa? Hindi ba yung ganyan? Okay bro. That's okay, dude. That's very hot. Very hot right there. No. 5, 4, 3, 2, 1. Yeah! Yeah, boy. Saksi mo ah.
So they were celebrating because it was the first time that the discharge was controlled to more than a minute. Because previously, when we ignited the plasma, the power supply would start to smoke, and that won't work anymore after the second experiment. But this one, it was a repeatable experiment, and it was possible to ignite the plasma. So now it was time to check if there's a copper deposit, because ideally we would like to have copper deposited on our acrylic substrate. And then since we did not have any X-ray diffraction in the university or SEM or any characterization tools, the quickest way was to check if there was an antibacterial activity together with the College of Veterinary Medicine. Unfortunately, it did not give any prohibition zone. So this is an E. coli plate. And it might be that the copper wires that we are using were not high quality, or it might be that it's mostly oxidized in the chamber because we're only using low vacuum. So there are many things that needs to be considered, but we are looking for ways on how to make this deposit better and show that it does have copper onto it. So my student Mark, he wanted to check other designs, and he found this one and tried it himself. So he's using a mug, and he created a hole on top which he can close for vacuum, connected an electrode on it, and also bias the bottom to create this dish.
Yeah.
Okay, so that is for the mini arc plasma. We have yet to create deposits onto the substrate, and we also are looking into checking for the results in the future weeks. Now let's move on and check the atmospheric plasma.
Careful na, careful. You know? Plasma jet. Plasma jet, huh?
Okay, so this was the device that I showed you at the beginning of my presentation. And when we were able to ignite this plasma, tests on rice irradiation was done. So this is my student again, and he's doing this initial experiment. So this is not the final experiments. He was trying to see the positioning, and also how he's going to run the long-term tests in the future. So these are initial testing. So for the variable parameters, we're actually going to check 4 different types of rice. And we're going to check the exposure distance, which is in centimeters, and also check the exposure duration, which differs in seconds. So some of the samples were exposed for 4 seconds and 6 seconds. Fortunately for us, we are right beside the Philippine Rice Research Institute. There are only 2 research institutes of rice here in Mindanao, and one of them is here in Central Mindanao University. And together with them, they have provided us with the rice variants. So before, when we were trying to design our experiments, our goal was to go to a farmer, and this farmer is going to give us his rice products, and then we're going to test his products. Unfortunately, when my student Che was trying to do the experiment, he found that the variants are not the same. So since it's coming from different sources, and he checked the rice, they are not uniform. So it was not a very scientific way. So it was better to go to a research institute so that we can have reliable sources of rice variants. So after 6 days, we observed the treated and untreated rice. And as you can see, the untreated rice is much shorter as compared to the treated rice. This is very useful for agricultural applications. And in fact, some studies already started irrigating corn seeds, and hopefully we can also use this with other types of seeds and grains here in Bukidnon. So these are just initial results, and they are already promising, and we have already planned a thorough experimentation. So in summary, plasma sources can have a variety of applications, and these are zinc oxide for solar cell applications, photocatalytic titanium dioxide for bactericidal application. We can also use it for hard coating. We can also deposit metal insulating transition vanadium dioxide and electrochromic windows. We can also use it for basic research on tungsten disulfide and moly disulfide, 2D layered materials. And I didn't put the check there because we haven't deposited antibacterial copper on acrylic yet, but hopefully soon we will have results on that. And we have seen that we have generated, we have a faster rise termination when exposed to atmospheric pressure plasma jet. So these are my references, and these are my publications actually. And for the future outlook, we are vigorously looking for funding. I have already applied for the Department of Science and Technology. So this is our science department here in the Philippines. They are the biggest grant giving body by the government, and also applied for DOST institutional development grant and a collaboration funding with Philippines and Taiwan. The rest, we are aiming for submission in these grants, and we hope to strengthen local and international collaboration. For example, now we are strongly collaborating with National Sun Yat-sen University of Taiwan and Uppsala University. We are looking into industry partnership. For example, Ionotics AB is willing to lend us their high PIMS power supply for testing here in the Philippines. And we hope to apply grants for characterization tools such as X-ray diffraction, SEM, TEM, and Raman, and so forth. So the current practice right now is we create our materials here and then we send the samples somewhere else. It takes a long while because obviously these institutes will have to prioritize their own students, or maybe the device is not available, or it has to be under maintenance, and various other problems. So I think it's really better if we have our own characterization tools, and we are looking into scaling up our research towards commercialization. And these are our team members. So from Central Mindanao University, this is yours truly, together with my students. And we have other faculty members who are the panel members for my students' thesis. And we have Mr. Butanas, who is also going to do some plasma-related studies together with his student, Joven Bonjok. And as I mentioned earlier, Dr. Christian Mahinay gave me the design for the atmospheric pressure plasma. Our partners from USTP made the power supplies for us. MSU IIT will be will be doing the characterization for us, and our partner from USEP is our collaborator doing the statistical analysis of our research. Before I finish, I also would like to introduce to you Physics Meetup. This is also an initiative of our department. It's like what we are doing now, but the difference is that we invite other researchers to talk to Filipino students. And we have started this several years ago, and it has already been recognized and awarded by some grant-giving bodies. We also have one patent pending item used for instructional material. This is a 3D instructional apparatus for vector operation developed by Dr. Cecilia Bucayong. So we use this to teach vectors. And if you are interested, you may also scan this QR code here, or you may drop a message. So we just started commercializing this, and we hope we can reach international shores together with Dr. Cecilia's invention. So with that, I'd like to thank you for your attention. Muchas gracias. And that's my talk for today. Thank you very much.
Thank you very much, Michelle Villamayor, for a great talk. Very interesting talk. Thank you very much. I would like to take advantage to mention to the public that if the public has questions, please leave the questions, write the questions on those links where you were following this video. Just type the public can type the questions on the links that you have been following, okay? And now we are going to start with a question from the panelists. Before that, I have a short questions. Beforehand. You have presented the physical vapor reposition equipment, and you have induced a plasma by microwave, right?
Yes.
Yeah, and then you have deposited vanadium, right?
Yes.
And what is the advantage in the physical vapor repositions to inject plasma, and without plasma and with plasma? What is the advantage of the plasma atmosphere?
Okay, so may I just share my window? Can you see my screen now?
Not yet. It is, yes, now we can see.
Okay, so I'm just scrolling up. Okay, so here it is. So plasma, we use plasma to sputter out our vanadium. And without plasma, there will not be any argon ions to sputter vanadium. So we will not be able to deposit our vanadium dioxide onto our substrate. This plasma is also used to activate our oxygen ions. And our oxygen ions will be the one reacting with the sputtered vanadium to deposit onto our substrate. So without plasma, there will not be any vanadium dioxide deposit at all. Perhaps there might be some evaporation techniques, but this technique I am not familiar with.
Okay, thank you very much. Because it is we usually have in Peru, in the University of San Marcos, physical vapor repositions, but it's by resistive. We evaporate applying a high voltage, and then and also sputtering as well. Yeah, nice.
Yes. Okay.
Thank you. Well, we are going to start with others panelists. We are going to start with the representative of the Sinvestab in Mexico, Professor Arturo Martinez. Arturo, your camera, please. Yeah.
Yes. Thanks for your presentation, Michelle.
Yes.
Thank you. I have a question for the vanadium oxide.
Yes.
You show the transition, the metal insulator transition.
Yes.
Do you have any application of this?
Yes.
material?
So one of the potential application of this is that it's going to be used for passive thermal control onto microsatellites. So you don't have to switch on and off. So it's only going to sense if it's too hot or too cold. So if it's hot, then it's going to activate its own cooling system. And if it's too cold, then of course it has to save its energy and then use the rest of its energy into something else, or like save it for other applications. So the passive switch is one of the applications. Unfortunately, the switching is too high. We have to move it a little lower to be more applicable. And this is where the research is going to. We dope several types of materials onto it so that the switching will have to go down. Unfortunately, my postdoc has ended, so I was not able to do any switching at lower temperatures, but this is actually the long-term goal of the project.
And the temperature, the lower, what is the lower? The lowest.
The lowest, for the meantime, I think it's 63 degrees Celsius, but lower than 63 is the best. I think they are aiming for 55 degrees Celsius.
Okay. Thank you very much for your time.
You're welcome.
Thank you, Arturo Martinez from Simvestab, Mexico. Now we have a panelist who is invited for today. Is Sergio Martinez from the University Autónoma del Carmen de México, from Mexico. Sergio. Sergio, are you there? Sergio Martinez. Okay, we can continue with other then. Okay, let's continue with from Brazil, from the representative of the Federal University of Pernambuco in Recife, Brazil, Professor Albino Aguiar. Albino.
Oh.
Hello.
Hello, Michelle Mahi. Congratulations for your talk, and also congratulations for your work. You have done already in very short period of time. You mentioned that you started in October last year, and it's amazing that you succeed having putting things to move. So I'm glad to see these young people doing this. Yeah, I would appreciate if we can collaborate. So be free to contact me. Luis will send you my email, or I can send you via chat. Yeah.
Yes, thank you very much.
We do have some facilities at our lab and at our department here in Recife, Brazil. So you can count on Sam, Tem, Raman,
yes,
and very soon solid NMR for solids.
Okay, thank you very much.
And
yes.
Also magnetization and as function of temperature, field, and frequency.
Yes.
What more? Heat capacity and resistivity measurements. So you be free to contact me. I was very impressed how you succeed with low funding. Yeah, very, very small funding.
No funding.
To the sputtering machine. So we do have a sputtering machine here.
Mm-hmm.
And I have a proposal for you already.
Yes, perfect.
Can you grow niobium titanium? Sorry, niobium tantalum or niobium vanadium multi-layers?
As long as we have the proper targets, then definitely we can find these parameters for you.
So I'll let you with this proposal.
Yeah.
Please be free to contact me. And again, congratulations for your work.
Thank you very much. Thank you very much, Professor.
I will get from Luis, our General Secretary, your contacts, and then I will contact you.
Okay, thank you. Luis, thank you, Professor.
Do you agree with this?
Yes, definitely. I would just like to mention that I wouldn't have been able to do this without the hard work of my students and also with our collaborators. So I'm actually quite lucky to be surrounded by such talented and hardworking people as well.
Yeah, it's always like this. My good colleagues and the bad colleagues, they always say, Albino is always at the beach and the student working.
Oh, okay? I see.
I would like to continue at the beach and production.
Okay.
Okay.
Yes, Professor.
So, nice to meet you. Congratulations
Thank you very
again.
much. Thank you very
Luis?
much.
Thank you very much. Luis.
Okay, thank you very much, Professor Albino Aguiar from Recife, Brazil. Professor Albino also has some funding from students, I think, for visiting in Brazil. Okay, I think that already Sergio Martinez is already online, I think, has recovered his signal from the University Autónoma del Carmen in Mexico. Sergio.
Thank you. Thank you. Congratulations, Michelle, Marie.
Thank you.
I have a question. What is the influence of the magnetism in the science of the materials? What is the influence of magnetism in this magnetometry spectrum in the process?
Where we position the magnets, do you mean?
Yes.
Okay, so I'll just share my screen. So for our most recent work, the magnets are actually placed underneath this orange material that's actually copper. We don't have a photo of it, but it's actually the shape of an annular and a cylindrical magnet. So the annular magnet is on the sides, and the cylindrical magnet is in the middle. So we will have a magnetic field which looks like a donut shape or toroidal shape on top of this copper material. I did not show this anymore here, but the magnets are underneath this material for this particular design.
Okay. Okay. Thank you very much.
Okay.
Congratulations.
Thank you.
Okay, thank you very much, Sergio, from the University Nacional del Carmen, Mexico. Now we continue. Let's go to Chile, in the south of South America, with very south in Chile as well. In Puerto Montt, Chile, the University of San Sebastián, Professor Felipe Mundaca. Felipe, your camera.
Hi, Michelle. Thanks for your lecture. With respect with vanadium oxide, in sputtering, is possible to do material in vanadium oxide?
Yes, it is possible to dope this material. So you could either use a different target and then bias it very, very little, or you could also like create a thermionic emission. So you can, from the magnetron sputtering, then you make a tungsten, like a wire or whatever material, metal dope that you would like to have, and then turn on this resistive wire, and then you will have some sort of doping during the vanadium dioxide. You could also use an ion beam. So when I visited Barcelona, Spain, we used an ion beam of different doping material. And yeah, so these are the things that you can do in order to dope your vanadium dioxide.
Okay, and other question, with vanadium oxide, when you apply temperature,
Yes.
I know the electrical property change. What are the reason for that? What property of the vanadium oxide change?
I think in order to create vanadium dioxide, you have to have a certain temperature. Otherwise, it develops into a different type of oxide. So it doesn't reach this VO2 oxidation state. It creates a different type of VOX material. And that is why it's very specific that it has to reach this temperature during the deposition. This is what we have observed previously.
But the electronic property, like band gap, change with temperature when you apply?
Okay, so with the band gap, I'm afraid so do you mean during deposition, or is it during when we heat it up or not?
When you apply temperature.
Okay, so not during deposition. Yes, the thing is it changes into a different phase. So it's vanadium dioxide R type, rutile, I think it's rutile, and then there's vanadium dioxide M1 and M2. So they shift in the electronic structure, the crystal structure, so the electronic structure also changes. So this is the reason why vanadium dioxide transitions from metal to insulator.
Okay. Well, thanks a lot for your presentation. Bye.
Thank you.
Thanks.
We do have a publication for that, and I can share it with you.
Okay, thanks.
Thank you, Professor Felipe Mundaca from the University of San Sebastian, Puerto Montt, Chile. Now let's move to London, in UK, with University College of London and the University of Cambridge, Professor Stuart Holmes. Stuart.
Thank you, Dr. Villamayor. Very interesting talk.
Thank you.
We've had lots of questions about the vanadium dioxide, so I'll try and avoid questions about vanadium dioxide. I was going to ask you some questions about that, but I'll stop because of the other panelists. Could you tell us something about the uniformity? If you sputter a film in an oxygen atmosphere, what's the uniformity of the film? Is it very uniform, or does it vary? What would be the answer to that?
So it depends on the parameters that you are using. So for example, if you have a chamber and the pressure is not good, let's say, it gives a non-uniform deposit. So this actually varies. So how much power you are also putting onto your target material. I think it's really a play on different parameters. So for example, if your oxygen source is on the left side of the chamber, and if you do not have the proper parameters, then obviously you will have a non-uniform oxygen deposit towards your sample. But at certain parameters, you might lower the base pressure, for example, or you would like to lower the flow rate of your oxygen, or you would also change the ratio of your argon and oxygen. Then by playing around these parameters, then you would get a deposit. Another technique would be to rotate your sample. So you only have a very stable oxygen source on one part of the chamber, but then obviously it's not going to be uniform all throughout. So the solution for that is to rotate your sample so that it will have an even deposit after the deposition process.
Thank you. I have one further question, and that is, do you ever get kind of implantation effects? You're depositing a metal somehow. Does it ever implant into the substrate? What would be does that effect occur? Perhaps?
Yes. So yes and no. Again, this is also depending on the parameters that you are using. So inside the chamber, if you have a very relatively high pressure, then our ions that get sputtered out, they would be losing their energy along the way, because it will be interacting with a lot of particles along the way, and then it will just like stay there and not implant. But if you have a very low vacuum or high vacuum, I mean, so the path of your sputtered material is very long, and it also gathers energy, so it will have a high chance for it to be penetrating onto your substrate. Now, the reason that we were able to create 2D layered materials is because we used high pressure. So our tungsten disulfide and our sulfur actually was not bombarding onto the substrate, but it was just like flowing slowly, and then with the high temperature, it was able to create this very nice 2D layered structure.
But thank you for those for answering those questions. Very interesting talk. Thank you.
Thank you very much.
Thank you, Stuart. I think that was online Professor Isaías Gonzaga from the Federal Rural University of Rio de Janeiro in Brazil. I don't know if it's still connected here. Isaías, are you there? Oh, he sent a message saying that has a problem to connect back again. He sends his apologies. Well, these are some members of the Latin American community. Now we are going to check if there are questions from the public of Colombia. Okay, let's go with Ximena Velázquez and also with Eliana to check if there is a question from Colombia. Okay, Ximena.
Sí, profe, estaba revisando aquí algunas redes y por este lado no tenemos preguntas. Creo que tampoco por el lado de Eliana. Sin embargo, Eliana, ¿hay algunas preguntas por ahí?
Well, no questions from Colombia. Now let's move to Peru. Melvin, are there questions from the public on the webline from Perú?
Saludos, gracias, profesor. No tenemos preguntas como tal, solo felicitaciones por su gran exposición. Saludos, gracias.
Okay, but I think, Melvin, that there is one. Michelle, I will read one from the Peruvians in the page, okay? It says from, I will read, Dulay Reciel. She said that, or he said, I don't know, they said that they are watching from Balay City, Bukidnon, Philippines.
Yes, so they are from my place. I live in that area. I'm actually in Balay City. So
yeah. They send greetings. Okay, I think that you have invited some of your public that are online. If one of your public has a question, please raise their hand and start the question.
So, so for anyone in the Philippines, if you have any questions,
they are online here. They are online in this meeting.
I think they are shy. I hope they're not that shy.
Filipinos are not shy. Pinag-isipan pa ba yan?
Pinag-iisipan pa ba yan?
Saint Paul. Okay, Saint Paul. Well, Eliana Marcela Vargas. Eliana.
Okay. So, I'll just share my screen. Can you see my screen now? Okay. So in order for us to see the effect of plasma, what we intend to do, I'll just go to that slide. Okay, so what we intend to do is actually measure the length of the roots and also measure the length of the shoot. And if just by visually looking at this, we can see that the plasma-treated rice seeds have longer shoots and they have longer roots. And this is telling us initially, as our initial experiment, that the effect of the plasma can actually be seen visually. But these are just, as I mentioned earlier, these are just initial experiments. So we are intending to do a more thorough study on this. So the idea is that we are currently just focused on the speed of germination. So these seeds were planted, or let's say exposed to water at the same time, but one sample set was treated with plasma and the other was untreated with plasma. And after 6 days, so this is just a 6-day observation, we have seen that the ones treated with plasma has a longer chance. I mean, they have a faster germination rate as to compared with the one with the untreated rice seeds. So this is very important because for a country like us, which are very dependent on rice, we are actually experiencing rice shortage. So even though we have a Philippine Rice Research Institute, we still import rice from different countries such as Vietnam and Thailand, for example. And that is not good, especially for our food security, and also it's going to be a security issue in the future. So we are trying to, what we need to do is to increase the germination rate. And even though it looks small, like right now we are only running 10 seeds, for example, but if you can see that we have hundreds and thousands of seeds which can grow one day faster, then it will have a strong social and economic effect in our rice production. So I hope that answers your question. Wow, okay. Thank you.
Okay, thank you very much, Eliana. So let's check if there are the last question from the rest of Latin America, from, I don't know, Arturo Martinez from Mexico, Felipe Mundaca from Chile. Are there questions from any other side?
No.
No, aquí en Chile tampoco. No hay preguntas.
No. Okay, no more questions from Latin America then. Well, thank you very much, Michelle Villamayor. It was very nice talk. Now we are going to, maybe you have your closing remarks, maybe to say goodbye to the Latin American public, because he's streaming from many Latin American universities, no, from Mexico, Chile, Colombia, Argentina, Brazil, Peru, Venezuela, Colombia, etc. No, any remarks, Michelle?
First of all, I would like to thank you, Luis, for inviting me to this prestigious event. It was very heartwarming, and I'm also humbled by this invitation. And thank you for Latin America for having me and listening to my talk. I hope you also learn that we do science here at this side of the world. We are interested to continue our studies together with you. If you would like to visit us here, you are very welcome. And of course, for the young students out there, if you want to work abroad, travel abroad, and decide to come home, you can also do that, as what I have did, and do great, significant research as well. That's it. So muchas gracias, amigos.
Thank you very much, Michelle. Michelle, also, let me, you are invited for the next talks, because we every Saturday we invite some other people, and also to the public, to mention the next talks. Okay, I will mention quite briefly. Okay. On March 4, on Saturday 4 March, the talk will be from Yotao Singh from the Federal University of Fluminense in Brazil. In March 11, Saturday, the talk will be from Professor Duval from the University of Sao Paulo, also from Brazil. In March 18, I think that Professor Stuart Hormes is invited, one of his students, in Saturday, March 18, from the University College of London. On March 25th, the talk will be Magnetization, Dynamics, and Thermoelectric Effects on Flexible Nanostructures, which is Professor Marcio Correa from the Federal University of Rio Grande do Norte in Brazil. On April 1st, will be Professor Verónica González from the Universidad del Oriente in Venezuela. In April 22nd, the talk will be absorption of CO2 in fullerenes under the enfoque de la teoría de functional theory, DFT, and will be Professor Sergio Martinez from the University of Carmen in Mexico. On April 29th will be the talk of Professor Ignacio Villa from the Universidad Distrital in Colombia. On May 6th will be Dr. Jose Velázquez from DESI Synchrotron facility in Germany. Well, you are invited in all these talks, and also now what we are going to do is just everybody will open their camera, please, to say goodbye to Michelle Villamayor and to congratulate to Michelle Villamayor for the nice talk and to say goodbye. Everybody open their camera, please, and to see the Latin American people. Okay. Okay. Goodbye then.
Thank you.
Ciao, ciao.
Ciao, bye.
Bye-bye. Thank you.